My name is Henry, and I'll be presenting the task number 8, Sci-Fi Sound. First, let's read the problem statement. Problem states that tapping the helical spring can make a sound like a laser shot in a science fiction movie. We shall investigate and explain this phenomenon. So first, let's begin with a sound demonstration. Firstly, with the sound from the sci-fi movie. I'm not really sure if you heard it, but it doesn't really matter. We'll also reproduce the sound as meant by the problem statement. It should sound something like this. You can hear distinct sounds sounding like laser shots from science fiction movies. Thank you. Okay, so now let's look at what sound really is. We'll do this by creating spectrograms of various sounds, both in the movie sound and in the sound created by the spring. We can see distinct curves in the sound throughout all frequency ranges. The curves are highlighted by the green line. When we look at the curves closely, we can see that higher frequencies arrive first and lower frequencies arrive later. Thus, we can state that different frequencies have different velocities. Therefore, the whole phenomenon behind the sci-fi sound is hearing a sound that consists of frequencies, firstly of high frequency. A sound that consists of firstly of high frequencies and then lower ones. Okay, now that we know what the problem states, what it's about, let's look at the basic principle behind this phenomenon. By creating a simple tap on, for example, a table, we can see all frequencies arrive at approximately the same time. Whereas, by tapping the spring, we can see the sound that's spread through a bigger time period, consisting of many different curves in the sound. Therefore, as we stated, say that different frequencies have different velocities. This is due to acoustic dispersion. Acoustic dispersion is very similar to light dispersion, where frequencies travel at different velocities, and therefore we hear the distinct sound. This happens, for example, at the prism or the light beam. Okay, now we can go for our experimental setup. Our experimental setup consisted of a slinky spring with an amplifier at the end pointed at the microphone. The setup of the amplifier was the same as you saw. We tapped the spring at the end or at different positions throughout the spring with a metal rod. These are pictures from our apparatus. You can see the amplifier directly pointing at the microphone, and also the spring connected inside the amplifier to transfer the vibrations of the spring. At the other end, it was connected to a metal circle, so it could be suspended. We have suspended the spring through our whole laboratory as such. Okay, now we can go through our theoretical model. When we look at the slinky spring, we can see that this consists it can be modeled as segments of stiff steel bars. This will be modeled as weights connected by horizontal rods connected by springs. Now we can express the slinky dispersion relation, which will tell us how do frequencies affect their velocities. First, we look at the displacement due to transverse waves in the slinky. By examining this model, we'll find that the dispersion for longitudinal waves is a linear dependency, and thus the omega to k, where k is the wave number and omega the frequency, is a linear dependency. Therefore, the sound is non-dispersive. So, okay, what will the sound be? In fact, it's due to transverse waves in the steel line, and by accounting for the transverse oscillations in the x direction, we'll find that the omega k relationship is not linear. Therefore, the the sound is dispersive. Then we'll look at the dispersion relation and what it consists of. In our dispersion relation, there's the speed of sound of non-dispersed waves, radius of gyration, we'll get that in a moment, and the wave number, which is 2 pi divided by lambda. To the sound, well, there are 2 different velocities in a dispersive sound. One being the phase velocity, and the second one being the group velocity. The phase velocity can be calculated from the omega k relationship we just got, and the group velocity, since it's d omega divided by dk, can be presented as such. Therefore, when we know the group velocity, which will be the actual velocity of the sound, we can calculate the time for each frequency to arrive at the end of the slinky. This could give us a theoretical prediction of the arrival of different frequencies to the end of the slinky. By doing so, we can plot a graph of arrival times of different frequencies over time. Now, we can overlay such graphs to spectrograms we presented previously. We can see that by using equal values for C, we use aluminum and brass springs, steel and brass springs. We can see that our theory nicely overlays the curve created by the sound. But we can also see there are different curves in the sound, and now we'll be investigating them. Okay, so let's investigate the echoes in the sound. First, being the you can see that there are different distinct curves in the whole sound. Okay, so let's look at what happens when we impact the steel rod at the end, the slinky spring. By impacting the spring at the end, we can see one group traveling through the spring and bouncing at the edges. Then we can express the time for the end echo as such. With this prediction, we can overlay the end echoes in the spring to our spectrogram, and we can see that this only satisfies some curves, and there are curves that were still not satisfied by this, by the echoes in the spring. Okay, so let's look at what happens, what was the phenomenon behind different echoes. We had the geometry constant radius of gyration. In our, it should be d divided by root of 12. We had the geometry constant in our relation. Therefore, we assume that the dispersion relation is geometry dependent. Thus, by tapping the spring in one direction, we should hear a different sound than tapping the spring in the second direction. Okay, so let's look at this phenomenon. By plotting the dispersion relations for different taps from different directions, we can see that we satisfy all of our curves in our spectrograms. Okay, so we'll try to isolate oscillations in one direction by only tapping the spring in one dimension. We can see by doing so, we still can isolate the oscillations in the second directions. Okay, so now let's move the point of impact somewhere in the middle of the spring. By doing so, when tapping on the spring, we create two groups traveling through the spring and bouncing at the edges. We can express the ratio of arrival times for these groups and then base our prediction of the time of arrival for these groups. Yes. Okay, so here you see a spectrogram of sound created by tapping at the end of the slinky and tapping at 3/5 of the slinky. You can see that tapping at 3/5 of the slinky sound is a lot noisier. We cannot really easily distinguish curves as we can at the end of slinky. Okay, so we'll use the ratio of arrival times and different radii of gyration to predict all of our slope curves in the spectrogram by tapping in the middle. Okay, we can see that this successfully predicts all of the curves. Okay, next we'll look at the relevant parameters behind this phenomenon. One of them being the spring length will be shortening the spring by catching different curves of the spring. We can see now the theory nicely accounts for this by changing the length in the theoretical prediction. We also measured the time of arrival for one frequency in a still springy, and we can see that our data is nicely fitted by our theoretical prediction. Okay, so now let's look at how the material of the spring affects this phenomenon. We measured the velocity of the sound in the springs, and from doing so, we could we can see that the errors at the high frequency range are a lot higher. This was due to the fact that we were not really able to, we were still able to set the time with the same accuracy, but since the time of arrival was smaller at higher frequencies, then the error was bigger. From this, we can plot the dispersion relation for different materials, and you can see that our theory nicely predicts our measurements in the materials. Thank you. To conclude my presentation, we defined the phenomenon behind this problem. We brought a theoretical model and measured different dependencies on spring material, length, and yes, thank you.
So we're going to move straight on to questions of the opponents of the report by the opponent. And you're going to be the opponent, are you?
Yes, I am.
Yeah, so you can bring it on board in a moment, and we will start the clock for your questions now.
First of all, how many modes were observed in your experiments?
How
Just name a
many?
number.
Not really sure where this. Are you asking?
How many excitation modes? You talked about exciting the spring in 2 modes, but how many modes did you actually observe?
We observed modes in different.
Just name a number.
3, 2.
Okay, maybe we'll discuss this later. In your experiment, you showed a setup where you horizontally mounted a spring. How big was the heat angle?
The angle at the end.
The angle between 2 turns.
I'm not really sure.
Do you think it has an influence?
Tension has an influence on this.
Okay, thank you. Totally fine. And how big was the radius? The typical radius for your string?
6 to 7 centimeters.
What was the typical wavelength you observed?
We observed different frequencies.
And what do you think is a typical wavelength?
Well,
Do you have an
we just did both.
For a typical wavelength?
Well,
You measured different frequencies, and you could also estimate the typical wavelength.
yes, it would be a range of wavelengths.
A range? Okay, yeah. We will discuss on this later.
Yes.
You talked about in your theory that you assume a straight bar. So does that phenomenon actually work if you're not using a helix, but instead of a long straight bar?
Yes, it does.
Did you experiment the wave pattern?
No.
Okay. And what was your sampling rate you used for your spectrograms?
44 kilohertz.
And do you know your frequency response curve of your microphone actually?
Yes, we do.
So you do actually think that the relative amplitudes between the frequency play a much bigger role for the sound itself?
I'm not really sure I understand the
The
question.
relative amplitude between the frequencies might change throughout the phenomenon.
Due to the frequency response of the microphone?
Yeah.
It might.
Okay,
it does.
And you can estimate that. Okay. Yeah. Okay. Probably fine. Thank you.
Okay, time starts now.
Yep.
Okay, so hey ladies and gentlemen, I'm Mr. Beam, I'm from the team Germany, and I'm now going to be the opponent on problem number 8 Sci-Fi Sound. So first of all, in general, to the report, we like the report, you use nice visualizations of using animations and pretty compelling sketches, and you also showed a few spectrograms which are really sufficient to explain the behavior of the Sci-Fi Sound, to explain the phenomenon actually, what is certain the Sci-Fi Sound. You also then basically give a quite basic qualitative explanation using the dispersion of the mechanical oscillation. However, he didn't really refer to why the origin of the sound is really a mechanical oscillation. Then he didn't discuss the different mode types. I asked this in the clarifying question. She somehow excited it. helix, but he didn't actually verify that which modes actually traveling on the helix itself. He talked about bending modes, but there might arise other modes too. We'll discuss that. Then he tried to show the sound of the science fiction movie, also referring to the spectrograms, which he did very nice, and he explained then the downward chirp, which is mainly the sound characteristic of the laser sound. However, there was unclear what the third axis of the spectrograms were and how the ranges actually are, because it must be the intensity, but he didn't really mention any axis actually in any range. Then there were some missing parameters throughout, which I find pretty bad, especially the helix angle and the turn count, and also he didn't talk about bidimension, although he also estimated it theoretically, but didn't verify it experimentally. And of course, as I said earlier, there was an unclear origin of the sound, so where does the sound actually emerge from, especially when using an amplifier. To his experiment, in general, he did a nice basic experiment using a slinky and also attaching an amplifier, which however might pose a problem, as we'll discuss on. And he also measured the sound with a microphone, and he then also said in the clarifying question that he indeed was able to estimate the frequency response curve, which is quite compelling, and of course needed if you, however, measure the sound with the microphone. He also excited different modes, however he didn't really come clear about which modes actually propagate. There might be torsional modes and other modes arising. There was a missing insight in how the data was actually gathered, for example, which sample rate he used for his microphone. And he of course also didn't introduce this to his tapping, he just showed it tapping it by hand, but he didn't introduce how reproducible his setup actually was for the mean of the tapping. And he also didn't estimate some errors in the spectrograms coming from external noise, for example, which is just, a minor point. The most important point, I think, was that there was no estimation of the influence of the cross-section done, and only minor and it was only minorly discussed how the material influenced the propagation of the mode, and there was no direct measurement of the mechanical oscillation, which I think would be more sufficient instead of using a microphone and measuring the sound on the microphone. And of course he was uncertain about his helix angle and even showed us a very big helix angle in experiments, what might actually change the sound a lot. We will discuss it. To go further on in the theory, I already covered a lot of these points. He modeled using a straight bar, which I think is sufficient at some point, but he didn't really come clear to his assumption. We will discuss on that. And he didn't discuss the influence of mode couplings, which of course also refers to different modes, which we'll discuss on later. Maybe also the different polarizations of bending modes, which might arise. And of course there were the unverified estimations, and which I think was quite bad was he talked a lot about verifying actually with his theory different echoes, which are not different modes or different propagation modes actually, but only echoes. So he didn't actually theoretically only predict echoes in his system, which is not really compelling. So last but not least, I think the task was mostly covered and fulfilled, but there were a few unclear physical statements also in the clarifying questions. And we will discuss on that. First discussion point which will be, and I will now invite you to discussion, will be which mode is actually valid and the different modes which arise. Okay, so first of all you talked about the helix and you showed us where you tapped the helix. Yes. How did you tap the helix actually? What are the different ways? How many different ways?
We tapped it in different directions.
And what are the different directions actually?
The spring has two dimensions.
So there's
one
inner
one
axis actually?
Yes,
there might be one direction parallel and one direction wave.
Yes.
Okay, and you covered both?
Yes.
Okay. Maybe just we can draw this on the whiteboard.
Yeah, sure.
And you can get
the marker.
If you tap it radially.
Yeah.
So how does the wave actually bend the helix? Can you just point it and just draw it? Actually?
Well, it bends the helix in such manner. It bends up and down.
How does the wire actually oscillate?
You know, so we can see it.
Yeah.
Normally use the top board before the slide.
Well, if we look at one helix, the wire will oscillate as such, and at very high wavelength, the whole wire might oscillate.
Okay, so you say that high wavelength, the whole helix actually is oscillating.
Yes, it might.
Okay, it might. And does this also have an influence on the sound?
I don't think so.
Because?
Why? We didn't measure such relationship.
Okay, I think I agree with that because the frequency, the average frequency, which might arise from an oscillation from a global mode on the helix, might be too low to actually hear it.
Yeah, it won't create standing waves or something. If you're ahead and
no, I'm not referring to standing waves, but it's sufficient to explain that the helix itself doesn't have influence.
No.
And therefore, it's sufficient for you to actually model it as a straight bar.
Yeah.
But there might be two different modes, two different polarizations actually of bending modes in a straight bar.
Okay.
Can you just maybe draw them in? If you set it radially or parallel? Can you just draw in how the wave actually bends the wire?
Well, it bends it in different dimensions. If you look at the cross section of the wire, well, one would bend it in this direction, and one would bend it in this direction.
Okay, so it would actually look like this at one point, and there would be also, this would be the deflection of our wire, and it could be also polarized out of plane. So it could be also, in 3 dimensions, it could be not only about this axis, but it could be only about this axis.
I'm not sure
The deflection you're saying.
Yeah, it bends the whole wire.
And why is there no torsion, actually, or torsional modes arising?
Well, we didn't measure such relations.
Do you think that those could have an influence?
For this frame? No, I don't think so.
No. Okay. Yeah, I disagree with this point, but we have to become more clear about this. In your report, I think on slide 24, actually was, and on slide
24.
Yeah, and on slide 80, 24, yeah. Yeah, and you talked about the assumption of a straight bar, and I asked you what a typical wavelength is in your experiment.
Yeah.
So can you answer this question? What is a typical wavelength?
Well, this question I think is a bit irrelevant because we're working with different frequencies. Therefore, the typical wavelength
would be different. But what is the maximum typical wavelength? Because you're assuming a straight line. If I look at your helix, and we can say that the global modes of your helix doesn't influence the sound that much. We just have to state that, for example, the following relation must hold that the maximum wavelength, which is actually modeled, must be in the range of the turn length.
Yeah, I agree.
And does this assumption actually hold in your experiment? Because if this doesn't hold, you can't model the helix actually as a straight line.
We didn't explore this deeper.
I think you must have done this, or you could have done this, because
modeling
is as a straight bar might also decouple some oscillations. Because there might also arise some torsional modes, which you can occur, and also higher frequency modes. I think it was on slide 3 or on slide 5 where you showed us the spectrograms. And the spectrograms only reach to a frequency about 8,000
Okay, we sure can look at spectrograms with high frequencies. I have them in my appendix.
By the way, actually, what is the estimation on the third axis, on the power? There must be a third axis because your spectrogram, so you must have the...
Yeah, we were not really interested in the power of the sound. We did not investigate this phenomenon.
And it is not important at all.
We did not investigate it. We investigated...
But you could have put it in a bucket. Yeah, because it is sufficient for it to be. Okay, so maybe let's talk this point over. We said that there might be different modes actually, and you only observe those two modes, which I don't really think are two different modes, because I think they look quite similar. They could be also echoes, I think. A echo. So just a reflection in your setup, because
the echo of the we measured this and it wasn't the echo. We modeled the echoes and in the
so are those echoes or not? Because in the report you also showed in the spectrum.
I showed echoes, and you can distinguish echoes, which would, the second echo in here would be somewhere here. And this I'll show you a graph where we can see the echoes clearly. For example, here, this is where we investigate the echoes. The echo would be somewhere here, as we model in our theory, and the sound here was created by the oscillation in the different direction of being straight.
But at some point I must disagree, because those curves actually look very different from each other. And you told me that those are echoes, but they could also very well be just a second mode which might arise. A second mode which is not covered by your theory, which you can model.
And
so which therefore...
If so, I think it's covered by our theory, because we can predict those.
You can only predict those simple modes. If I refer what you actually discussed earlier.
Yeah.
We cannot predict what actually is about torsional modes or longitudinal modes or axial modes, which might come from
actually. But as you can see, we did not see such modes, and our modes covers everything we did measure.
Okay, maybe I have to disagree on this point, but maybe we become clear about if we talk about your experiment. Maybe you can go to the slide where you showed us your experiment setup. I think it was somehow on slide 2070 or 20, or no, it was 30 and 40 actually, 14 and 13.
14? Which one?
Maybe just go to the slide where you showed us your experiment setup.
This one?
No, in your report. Yeah, this one.
Yeah, okay.
Totally fine. And here you actually showed us how you suspended the string. And for me, if I just make this in whiteboard, the helix angle is actually defined as the angle between those two.
So the helix angle, well, it depends on the tension in the string.
Of course it does.
Yeah.
But does it influence the sound? Because it does indeed.
Okay, indeed, tension could influence the sound.
Could or does?
It does.
It does, okay, you investigated on this.
Yeah, we measured for different tensions, and for the tensions we created, we did not measure the serious difference in the sound.
So you didn't very systematically the helix angle actually?
No, we varied the slinky length with the length, but with the same tension.
And what is the result? How does the sound change if you change the helix angle? What is the result in your experimental investigation? Because you talked over that.
Well,
we have some results.
Yeah, sure. I'll show them. Yeah. Okay, I do not have spectrograms of that, but we plotted.
Totally fine. Maybe I just can make this point because I'm the opponent. I think the helix angle has a major influence, as you also referred to, because it comes from the tension, and it also changes the sound, the duration, and the pitch. I think.
Okay, we plotted the graph of the dispersion relation for different tensions, for our tension.
Sorry to interrupt you, but this is not what I'm aiming at. I totally get your point, but this is not the physics I'm aiming at. Sorry. And last but not least, you always use an amplifier in these experiments. And you didn't talk about the origin of sound. So you say the sound actually is created by bending of your wave. But then you attach an amplifier, and your amplifier oscillates.
Yes, it does.
There is somewhat a weak contact, so a coupling between. There might be cutoff frequency actually. And thus the amplifier and the mounting of the amplifier has an influence on the sound.
It has an influence, but the influence is quite low. Use the amplifier to be able to measure the frequencies, so they would be louder.
But in your experimental setup, you said, if you can just go back, you showed us that you just you picked up the sound with your microphone just at the amplifier. So you're actually capturing the sound from the amplifier, not the sound from the slinky. But the task requires you to capture the sound from the slinky.
Okay, I agree. But the sound from the slinky was not loud enough for us to capture it by the microphone in our experiments.
Okay, I get this point, but maybe the sound differs very much. Also the equals.
I don't agree that it differs very much. I agree that the amplifier might pick up some frequencies, but I don't think that the curves will differ.
But you talked about, also in the question you talked about the frequency response curve, and I think also the frequency response curve or the analytic amplitude will change due to the amplifier.
Yeah, I agree, but we didn't have investigation topics.
I'd like to invite
maybe
to summarise this.
Okay, so first of all, thank you for the discussion. Maybe to summarize the discussion. First of all, we talked about the tapping of the intelligence spring. And we covered that actually what he did in theory is actually what he also did in his experiment. He tapped in two different directions, therefore actually modeling two waves, two polarizations on the string, and we both agreed that the global modes of oscillation which might arise from a wavelength which just isn't smaller than 1 length doesn't have an influence because it just bends the whole helix, and the frequency of the bending of the whole helix might be not hearable. Then we talked about the bending modes and his assumptions actually, and he wasn't able to name actually a typical wavelength, therefore not verifying his assumptions. Then we talked about the different spectrograms and different modes, and I think what he pointed out is just equals and not a different mode. Last but not least, we talked about the
Thank you very much. So we move on to questions of the reviewer to the reporter and the opponent.
To the reporter, how did you distinguish background noise on the software you used to analyze frequencies?
We did not. We did not filter the different curves. We only overlaid our theory to them so we can see.
Did you account for tension in your models for both dispersive mediums and non-dispersive mediums?
Yes.
For both of them?
Yes. Well, yes.
Do you, the error bars you had included on some of your graphs, were they due to uncertainties in measurements or were they due to difference in trials?
You mean something like this?
Yes.
Okay, so for the lower frequencies, the time of higher frequencies, the time of arrival was very small.
Was it uncertainty or
yes,
trial
difference?
Uncertainty.
Yes.
Can you go to slide 21, please?
Yes.
Do you believe there is some sort of error between the theoretical and measure? What's the error? Like, what's the numerical error that you have found?
We were not able to measure the error.
Yep, that's fine.
So we did only overlay our theory.
Yep. How many trials did you take for every single measurement?
I'm not really sure where you're heading with this. So
How many trials were repeated?
We repeated our trials when finding the arrival times of one frequencies, but also for the dispersion relations.
And how did you determine the density and density or elasticity of the materials you used?
Well, we did not really need to calculate for this since we used the velocity in the material from the tables for brass and steel.
Could you go through it? Do you think that torsional nodes will be picked up with an amplifier? To the opposition.
Could you repeat?
To the opposition, do you think that torsional nodes will...
Torsional modes.
Will be...
all modes, all oscillations of the mechanics of the helix will be actually coupled to the amplifier and therefore also amplified.
I agree.
Does the opposition believe that the cup had any resonating effects on the frequencies that were picked up? The cup created some sort of resonance that was picked
the
up.
The amplifier, you think? The cup is the amplifier.
Amplifier.
Okay, yeah, the cup, of course, the cup is resonating with its own frequency response, actually with its own response curve, and therefore changed the sound in a really, quite big way. That's a big influence, which wasn't covered in the report.
Okay, time's up. Thank you very much.
Of the reporter, then the presentation of the opponent, and then through discussion. First off, to the reporter. What they did well was they had a live demonstration in front of us, which really clarified what the actual effect and what the sound heard would be. Their comparison with the sound that was made, that was seen during movies, was also quite good. Their theoretical model was provided. For all experiments, and it was plotted against their actual measurements. The explanation of the actual echoes was quite clear, but there were quite a few areas of improvements. That there were no numerical uncertainties included for their graphs of their frequency versus time graphs of measurement that were measured. The effect of tension was not explored in their formulas, and it was only constricted to a stiff bar. The number of trials was not originally mentioned during the presentation, and the experimental setup was not reproducible at all. The resonance was further not discussed. The resonance of the cup and the effect of it amplifying particular frequencies more was not discussed, and I believe that was quite important as it would have showed up as some sort of errors or difference in precision. Furthermore, the intensity was not the intensity of the tap was not investigated. The opponent picked up quite well on the mechanical vibrations, and that was the very base of how the sound was produced, but that was not mentioned by the reporter. They also picked up on how the experiment could not be controlled and reproduced quite well. That was seen in the reporter's presentation. And they picked up on which specific node was heard and which was creating the sounds similar to the ones produced in the movie. The area's improvement was that they also did not talk about the actual tension and effect, and that would have been quite important as a stiff bar would still have some tension in it, even though their theoretical and measurement showed that it might have been negligible, but any set amount of uncertainty that would have been shown would have highlighted that tension was important. They also did not pick up on the lack of error bars or error analysis on slide 46, where moving on to the discussion, the opponent picked up on the importance of the assumptions and what the effect that had on the max wavelength that would have been measured, and the fact that the report did not measure it. And we agree with the opponent. We agree with the opposition on this proposition. The opponent refers back to the diagrams that were drawn, that they asked the presenters to draw, and that was quite good. For errors improvement, the opposition starts off by talking about excitations, but why the lower frequencies arrive first, we believe will be more important. As that is the sort of basis of explaining how the actual slinky sound is heard and interpreted by us. We agree with the report that the procedural mode should occur, and the report had modeled his findings well. The opponent wanted to talk about mechanical vibrations and mentioned it in their but they did not actually go into discussion with this during the actual discussion. Thank you.
Thank you very much. Well done.
Okay, so as first, I'd like to get back to the amplifiers that were several times mentioned. Yes, we use the amplifier. The amplifier picks up various frequencies, but we were not interested in the loudness of these frequencies, rather the curves of the frequencies arriving. We in fact did use different amplifiers and tested whether the sounds reproduced were different. The lines you can see here were when the spring bumped into the cup, creating a tap like we explained in the beginning, as on a table. In fact, we did use different amplifiers. Okay. Also, I'd like to get back to tension. I think that the helix angle and tension are closely connected, and we in fact did try different tensions, and we can see this was when the spring was only hanging. Therefore, the tension was smaller, and we can see that our model, in fact, does also nicely fit this data. Yes, okay. So the reviewer asked about the reproducibility of our measurements. We in fact did do different measurements and measure the time of arrival of one frequency throughout different measurements through different lengths. Therefore, we can say that we did create a reproducible system if that was the way we were heading. We also stated something about about us not investigating why, where does the okay, it said something about frequencies arriving at different times. We in fact did explain this by deriving the dispersion relation, which states from which we can measure when do different frequencies arrive.
Thank you very much. Well done. Okay, about 3 weeks you can stand in the corner there. For questions from the jury panel. So, big jury panel, who'd like to answer the question? Yep, yeah, so, yes, please start with.
Can you again show the slide with comparison of your experimental director results?
Oh, do you know the slide?
For example, 16.
16?
The last one.
I'm not sure I have a slide 16. Oh, okay. What's this?
So, can you explain the difference between your experiment and theoretical results in the points of the maximal curvature of the curve?
Okay, so I think this is a small discrepancy, and we believe that this might be due to the Fourier transform of the sound, which could not really pinpoint the sound when it would arrive, rather it was a frequency of the time range.
Yeah, so in few words, can you tell us what's the physical mechanism of the echo?
Of the echo?
Yeah.
Well, the groove travels through the spring and bounces at the edge, similar to a sound of bouncing at, for example, a surface, and bouncing back to the amplifier.
So can you put the graph of what you actually say the echo is somewhere here, illustrate that phenomenon with your, well, you have several curves, right? No, not that one.
Okay, do you know the slide number?
No, really, there are several curves with different colors.
This?
When they ask you, when the opponent asks, right?
Yeah. Should I explain this graph?
Yeah.
Okay, so the groove velocities depend on the dimension of the spring. So there are two velocities. One is greater, one is slower. The greater one is the wider dimension, and the slower one in the
The higher frequencies would travel through the dispersing medium faster than the phase velocity of the lower frequencies.
This is oh, sorry. You don't. Yeah. Thanks. So for the reviewer, you said that one of the points missed out was that the slinky was wrapped around the cup rather than attached at one point. So can you suggest how that would have affected their results?
So in their experiment, they had the slinky wrapped around the actual cup. That provides multiple points of where the vibrations can go from a solid dispersing medium into air, a non-dispersing medium. And since there are different points of contact, the vibrations will travel into a different medium at different points, and that would have created a source of error where frequencies would be coming at a longer period of time compared to if they were just put into one point of the cup.
So, question for the reporter. So you have the slinky horizontally, right?
Yes.
Because when you show, you can see that the slinky part like
Yeah.
So for the opponent, do you think that affect the result
Yeah,
that you
it
got?
heavily affects the sound, I think, because it also varies the tension of the length and therefore the helix angle, and varying the tension would also vary the high duration and the pitch of the sound, because it influences the dispersion.
Yeah, we measured this.
Oh,
We found out that yeah.
Okay. So how about the reviewer?
We're out of time.
Oh,
Sorry. The presentation by Australia gave it a 6, 5, 7, 7, 6. Well done. So I gave the highest presentations from the judges, so I'll just say well done. That was a really fine start for the tournament. Everybody else to be quaked in the boots, really. You're thinking, well, you got 16 more of those, you'll be all right. Yeah, I thought it was very thorough. I thought at the beginning you were going to start telling us the sound waves were going through it, but you just must have said sound when you meant it's not really sound, the vibration that's going through the wire. But you made it fairly clear. You've got a lot of data which you've got experimental data fit into it quite well. Yeah, and it was nicely presented. I liked that you were not talking super fast, and you gave us time to read the slides. The mathematics was presented with us time to look at it, take it in. That was very welcome. So I was able to understand what you did. Live demonstrations always good. It's a very interesting problem, I think. Just keep digging into it, there's always more to do, which, yeah, so that's my summary. Everybody else gave it a 6 minutes. Does anyone want to talk about weak areas? Like what
I would have liked, just as a comment for future development, I would have liked to see more physical understanding. I mean, you did it, like the chair is saying, you did a good job comparing experiments with the theory I think the presentation was lacking on the inner physical mechanism of the old home. So that's why I gave you a 6. But that's, take it as an encouragement for future presentation.
So let's talk about the opposition. Did you give the 8? Yeah. Do you want to talk? You gave the 8 to the opponent.
Yeah, I think the opposition tackled they reported on very good points, and that's why I gave 8, especially the vertical horizontal component, the modes. You kind of answered that, but now I'm changing the position. The position picked up very good points, and that's why that's the role of the opposition. So I need to judge their understanding of the physics within your presentation. I think was quite good.
Are there any more feedback points from the opponents?
It was really good position, so even if it's like on the lower end, I think it was, I mean, my mark was 7, but I think it was really good with many, your opinions and your views, your physics that was brought in, that I think was really good. So,
Thank you.
I marked you slightly down for your conduct at the beginning. I thought you were a little bit super aggressive with your questioning, asking him for a number. Give me a number. Yes, so just be careful. And for the reviewer, we had a 7 and we had a 5.
yeah, I'm 5, and I think you started really well with the questions. I think I liked some of them. You picked up some points that were not discussed before. And at the beginning of your discussion, or your report of the discussion before, was starting really well, but then like you slowed down when I was hoping to hear the most from you on the covering how they discussed and how they agreed or disagreed. I think you mostly spent time like reviewing their short presentations, while I think your role should be more on the other end. So I think you missed some point on the way the spring was attached. I think it was obvious from the photos that it was like a single point attachment, while you were saying that it was all around the cup. I don't know. So that was for me. That was swinging it. My mark was like 5.5, like when I added all this stuff, and yeah, I needed to make a decision, and I went to 5.
And the 7, do you want to talk about the 7?
I gave a 7 to
So check
So, so Joe, my point of view was not excellent, but it's a good review. And so the questions was pretty good beginning, and so it's 1 point. So the review of reporting the position, I give you 2 points for both. So to my point of view, it was informative and contains that information that could be there. And so discussion is 1 point, and nothing to subtract, and occasionally it's 7.
So, great start, everybody. So we are back in here in a moment for the next round. 3 minutes.